concentrated in the 1 to 10 hertz frequency band. And it's part of a family of a map of tremor locations from the UW group, and which are color-coded by time, and it illustrates this point that most of these episodic tremor and slip episodes nucleate down dip and migrate up dip, and then they migrate along strike. And they have a typical speed at which they migrate, which is extremely slow for seismic phenomena. Also in this region, which is a portion of Cascadia, the magnitude range is fairly constrained to magnitude 6.5 to 6.7. So we have an earthquake of this magnitude but lasting several weeks, and it happens every 12 to 15 months. I think most of you are familiar with that. I'm not going to go through this slide from Rubinstein at all, but it illustrates how tremor can be triggered by surface waves from distant earthquakes. And analysis of this indicates that very low stresses of 20 to 40 kilopascals, which are much, much lower than any ambient stresses, than ambient normal stresses or mean stresses in the tremor zone, do trigger tremor, which is illustrated here. And what we're going to see is that tidal stresses far lower than this also trigger tremor. So actually this has been known for some time, and there's a number of papers that indicate that both tremor and slow slip are triggered by tides. And here's an early result from Obara-san indicating the correspondence of ocean water level with tremor bursts over maybe a week here. So to talk about my analysis, first I'm going to talk about the slip pulse nature, which lets us define an ETS tremor front. And then I will talk about the influence of tides and get these three main conclusions, which we will return to repeatedly. And this is really something happening during these large magnitude 6.6, more or less, ETS events. So to get oriented, here's a time distance plot for about 4 years, along the Cascadia margin. And we see that there are large ETSs every so often. And in fact, their recurrence intervals vary along strike, but over a big range of strike up here in northern Washington, southern Vancouver Island, it's about 14 months. We also see from this plot that there's a lot of small, actually it's hard for you to see, there's about 40% of the tremor is occurring between these major ETSs, and I'll have something to say about that at the end of the talk. So here's one of these large ETSs in 2010, and we see again it initiated in an area where they tend to initiate, down dip, it propagated up dip, and then it propagated along strike. And looking at these colors, which indicate the time, which spanned about 4 weeks, we can see the slip pulse nature of this ETS. So in 2011, I had a Nature Geoscience paper where we also see the slip pulse nature of 5 large ETSs in the same region. And here we have time distance plots. So this is time, 3 weeks, and this is distance along strike, so projected onto this black line here. And these are little map views of these 5 different ETSs. So they were not identical, but they were similar in many respects. And this time distance plot indicates that when it's slipping up far to the north, when it's tremoring up far to the north, that is, it has ceased tremoring farther south, for example. There's a lot of information you can get from these. And one of the most interesting ones were rapid tremor reversals, which are little episodes where tremor travels back the opposite direction from the main main slip pulse traveling along. Oh, okay, by the way, please interrupt me if you have questions and things need clarification. I think that would be fine. Now, so I termed these rapid tremor reversals, and they travel about 25 times faster backward along the region that has already broken. So they're basically going along strike, and they're much faster going backwards than the slip pulse is advancing forwards. And in fact, it's going to turn out that they are sensitive to the tides. And so here we had a paper in GRL of 2013, which looked at our array of arrays, our special deployment called Array of Arrays, where we had 8 subarrays in northern Washington, and we got higher resolution locations than our general locations. Our general locations are from envelope cross-correlation with the method of Weck and Krager, and they're available online in a very nice website that we have. And anyone can pick them up. But these array of array data are different. You can actually get them from IRIS. But what we have here is a time, 3 days, distance plot, so distance along strike through here. And we can see the behavior of the tremor here, and you can see several rapid tremor reversals occurring during this 3 days when the tremor was under the array, and we got more precise locations. And we can compare it to shear stress changes from tidal loading and amplitude of the tremor, basically. And these are located with a different method, namely beamforming. Yeah, just speak up.
How did you compute that stress evolution associated with tides?
These tides. I will come to that, actually. It includes solid earth and ocean loading tides. And so we see correspondence, which is kind of washed out here, it seems like, between when the rapid tremor reversals are. Wait, here we can see it maybe better. And basically, we have these rapid tremor reversals at about the same time that tidal stress is encouraging slip on the plate interface. So shear stress is high on the plate interface from the tidal stress.
Heidi,
Yeah.
Sorry to interrupt you, but you need to use the mic because it's being broadcast.
Oh, all right. And we also, at the same time, have high amplitudes occurring. So these high amplitude rapid tremor reversals occur during positive tidal shear stress. Now, I want to talk about the tremor front. So this shows time distance plots stretched out in a different way. For here we have about 6 weeks of time and distance along strike. And we have on here 7 major ETS events. And we can see the propagation. And I can define the start of the tremor with this black line. So it's objectively defined from this data. Now, I want to focus in the region between these dotted lines along strike, which is about 100-kilometer region long, and which has been repeatedly swept by ETSs with a fairly simple structure. And what I want to do is lump together all tremor close to the black line within a day and a half of the tremor front, and all tremor after that into 2 groups and analyze them separately. Then I want to break it into 3 groups to analyze separately to see if properties of tidal sensitivity are changing at a given location as slip accumulates. Now, there's a lot of evidence that in Cascadia, the slow slip and the tremor are co-located, and only a few % of the time are they separate from each other. So I'm going to ignore that and use the simplicity of Cascadia to basically say that if tremor is occurring like this, we're pretty sure slow slip is occurring at the same time and driving the tremor. And I know that you have a more complex situation here. Okay, so to zoom in and look at this a little bit more closely, here darker blue means deeper, and we can see the tendency so this is the initiation of this ETS. It initiates deeper, and as it propagates, it gets a little shallower. But that doesn't always happen. So in 2012, it initiated shallow and propagated a little deeper, and then propagated a long strike, and it passed through this region of our area of study going south instead of north. But that doesn't matter for me because I'm going to lump together all the tremors near that black line within a day and a half of the black line, and all the tremors after that. So I'm going to group all the tremors relative to a tremor front. And we can actually compare these tremor fronts, which I'm doing here. And in order to compare them and sort of get an idea of their average velocities, I reversed the 2012, which went south through the area. We can just look at the slopes and see that they mostly have pretty similar slopes, except for the yellow one. And the slope is generally actually less than 10 kilometers a day. So one of my little pet peeves is the velocity is really a little bit less than, the average velocity tends to be a little less than 10 kilometers a day. Also, the south-going arm, which some of them have, is slower still than the north-going arms. Okay, so that's sort of a comparison. Now here I have a histogram of tremor, the time that tremor occurred after the tremor front passed by an area. And so this is 5 days across here. And I've lumped all the tremor together, so this is about 33,000 tremors. And from this and from other information that I'll probably present more on Thursday at the workshop, we infer that slip at one location continues, perhaps on and off, but for several days. And it has this interesting asymmetric shape. And that is reminiscent of a slip pulse, but it needs to be flipped here. This is from a paper by Alan Rubin. So this asymmetric shape is rather reminiscent of a slip pulse. And so this led me to ask the question, does the fault weaken during this period of time and become more sensitive to tidal stresses? And so the data of this study are all these tremor locations from 6 different ETSs between those dashed lines. And they cover this region. And I'm going to combine tremor from different fault locations, different ETSs, 6 different ETSs. I'm going to combine them all given this tremor front time. So if there's any questions, you can ask. Now, how do we get these tidal stresses? Well, they include both the solid earth and ocean loads, so the solid earth from the sun and the moon. And basically they're computed from Duncan Agnew's Spottle code. And I'm following the method of Hawthorne and Rubin, and in fact, Jessica Hawthorne was very helpful in doing this. They include the 5 largest tides, which are these, and they include the geography of not just the Pacific Ocean, but regional bodies of water like Puget Sound. We get a full stress tensor, and it is the stress change due to those tides. And we resolve it onto a plate interface, into shear and normal on a plate interface using the McCrory plate model. And we can also get the mean stress, which is distinct from the normal stress. Yes? Which is bigger? Yes, in many locations the ocean tides are bigger. It depends on the geographic location relative to Puget Sound, and we'll see that actually. So This is a study in the time domain, so I compute the values every 10 minutes on a spatial grid. So I'm computing these stresses, the whole stress tensor every 10 minutes, and this is the grid I use. Now, the idea then is to compute that stress change and put it into Coulomb stress, so I don't have to consider normal and shear separately, but I'll use various coefficients of mu and see what works best. I'll compare the numbers of tremor during the positive and negative Coulomb stress changes on the inferred fault plane, and I'll study how sensitivity evolves at an average spot. And this, so evolves is important because it's changing over the 5 days, and average spot is important because I've lumped together the entire region. And so I'm really talking about macroscopic properties of both slow slip and tremor together as a unit. So I envision that there's slow slip going on, there's tremor asperities embedded in the region that are triggered as soon as the slow slip occurs adjacent to them. Typically they're so small they get stressed very fast with even a little bit of slow slip. So this is a macroscopic kind of study lumping together the tremor asperities and the slow slipping region. So I need to review this Coulomb failure function so you understand why I'm able to get intrinsic friction. So Coulomb, the change, so this is all about stress changes. The change in Coulomb stress is the change in shear stress plus the intrinsic friction times the effective normal stress. So this would be the normal stress plus the pore pressure change, which is acting against the normal stress. And the simplest assumption for the pore pressure change would be that it's some coefficient times the mean stress. This represents the mean stress. And this is appropriate for undrained conditions, which people think is the most appropriate for tremor, for this type of stressing, which changes every 12 to 26 hours. And this Skempton coefficient is actually, it's a property of a hydromechanical reservoir. It's pretty complex, and it indicates its behavior under, it indicates the pore pressure change under stress change. So it's actually something that deserves further study. But this is the kind of simplest way of viewing it. So, however, in contrast to this, a common assumption is that the pore pressure change is this coefficient times the change in normal stress. And this has been a common assumption because it's simpler, but in fact it's not necessarily correct. They are not equal to each other. But if you make this assumption, then the Coulomb stress change looks like this, because you put in this for pore pressure here and you have a normal stress. So it ends up looking like this, and all you can get out is an effective friction, as it turns out.
Heidi?
Yeah.
Do you mean normal stress? You mean the normal traction to the interface?
The change in normal traction on the interface due to tides.
So,
It's a small change relative to any various ambient stresses.
right. Yes, a Skempton coefficient, which is a good, as you explained, approximation to quantify what would be the change in pore pressure in undrained conditions, depends on the confining pressure change, not the normal to a surface stress.
So we're talking about stress changes producing pore pressure changes. And
I mean, that equation, just for me to understand
what, this one
that one, yes, the delta sigma
is the
is
normal.
a change in the normal traction.
Yes, that's right. And this is an assumption that is made, not by me, but in fact, Okay, I will talk about this more later in the talk. And maybe we'll return to it. It's a very complex situation because in reality this is not a coefficient. If you have an anisotropic material, it can be a tensor. And one of the things I've proposed to do in a funded NSF grant is study this and see if these are two end members of a situation. And I want to study this and see if some behavior in between these two end members might in fact explain the data even better. And in which case I will be using a Skempton tensor. But we can talk about that later, I think. Okay, so if this assumption is better, is more appropriate for our situation, then we're only going to be able to get an effective friction. If this assumption is better for the situation, I'll call this model 1 and I'll end up calling this model 2, we'll be able to back out intrinsic friction because this mean stress is distinct from this normal stress. They are doing different things in time because we have, we have an elastic material over these time scales. Okay, so we'll return to talking about this, but I want to address this issue. How different are the normal and mean stresses due to tides? So here's a specific location where I've plotted the difference between them, the normal stress minus this mean stress. I call it volumetric, but it's actually the mean stress. And this is in kilopascals. And in order to, for reference, I plot it versus shear stress change in kilopascals. And you can see it gets quite large. It gets up to 4 kilopascals, which is bigger than the shear stress range. So you cannot just blindly make this assumption. It's in this region, it's quite a poor assumption to make. The X just divides this into different regions. Okay, so we won't make it. We'll consider two different models and see which is better. So I want to illustrate how the stresses can depend on location relative to a body of water. So this is the Strait of Juan de Fuca going into Puget Sound. So this is water. At these different locations, I have computed tidal stress, and we can see how it is different in these two locations here. And I've plotted normal stress versus shear stress change on the interface. And normal stress here, I have compression is negative, so compression is over here. And I'll have that the whole time. And we can see the behavior depends quite a bit on location. So this is 3 months of stress going around this so-called stress trajectory. And as I said, negative is compression. And we want to view this in the context of Coulomb failure. So hopefully you're familiar with Coulomb failure where you plot shear versus normal like we're doing, but we need to flip it like that so that greater compression is negative. This is the engineering convention and what I like to use. So here's a Coulomb failure line, and essentially we don't know the absolute location of the stress. We don't know the ambient shear stress or normal stress, but we do know this little ellipse, which is supposed to represent this or whatever is appropriate for whatever location we're at. We do know a bunch of them, and we do know this where on this ellipse a given tremor was when it occurred. So we don't know the location of this shape, but we know the shape itself pretty well, and it's different for different locations over the fault.
Excuse me, this difference that you show, normal and shear stress in these two places over 3 months, so this is reflecting the water body?
Yes.
Well,
No, not entirely. It's the change of the sun and the moon. So this relation of the sun and the moon change every 2 weeks.
right, but you're looking at for 3 months, so there seems to be no similarity.
Either two different locations. So actually we can go to the next one. Okay. here are for all six locations. So shear versus normal follows these different paths. These two are far from the water. These two are close to the water.
So it's the water.
The water is responsible for the difference between these. Yeah.
Yeah, otherwise, if you do a tide there, tide should be similar. At least very close by this. The time shifts, I guess.
Well, the tide is moving in and out of here, and it takes an hour or so or more to get through here. This is what it does. It's pretty complicated. So this shows the value of this kind of time domain approach, including 5 different tidal components. Looking only at M2 is really not enough, because the other components interfere, and the interference changes over weeks. So I probably should show a time series, would make it a little bit clearer. And one will come up at the end of the talk, but I should probably put one in here. Okay, so the point of this is just to illustrate that the geography matters, and we have to compute the tidal stress separately for each location. And of course I use this finer grid. Okay, so given that I have all these elements, I'm going to divide my tremors into the 2 groups, like I told you, illustrated by blue and magenta here. And there's about 13,000 in this so-called early group and 21,000 in this later group. And so what I do, so this is something I need to explain. So it's color-coded, so dark blue is the early group, magenta is the later group of tremors, and I've plotted on the horizontal that Coulomb stress change due to the earth and ocean tides. And it goes up to 3 kilopascals and negative 3 kilopascals, which would inhibit slip. And this is actually in the direction of plate convergence. Is the shear stress is calculated in the direction of plate convergence. It's a small detail. And on this axis, I have a ratio called the normalized frequency of occurrence. And so we can view it as the fraction of tremor in each stress bin. So each of these is a stress bin, relative to the fraction of time that the fault spends in that stress bin. So I need to kind of calculate this for every different location and add them all up and make sure I've normalized properly. And I see this big contrast in behavior between the 2 time periods, namely that the early tremor is insensitive to tidal stress. The ratios are all near 1 here, whereas the later tremor is sensitive to tidal stress, and it's inhibited where the tidal stress is against slip, and it's promoted where the tidal stress is encouraging of slip in the plate convergence direction. And in fact, this is following roughly an exponential shape. Now, okay. So this shows this striking change here. But let's go on and divide it into 3 groups, indicated by the blue, cyan, and magenta groups here. And then we do a similar kind of analysis, and we see an even stronger, so this is a steeper exponential for the latest group. So the early group is the same as before, and the latest group here, the magenta, is even stronger than before, and the intermediate group, the cyan, has an intermediate amount of tidal sensitivity. So I interpret this to mean that the tidal influence, it clearly means the tidal influence grows, and I interpret that to mean the fault continues to weaken for several days after the start of slip, because this is 5 days across.
Just to understand that, so there's no notion of time in the picture to
There's 3 time periods presented here.
Right. So for instance, yes, but if we would like to see how the tide or the tidal influence, the Coulomb failure evolves in the last phase, in the third.
Within here?
Yeah, for instance, yeah. How,
We can divide this more finely, but the more finely we divide it, the fewer tremors we have that we're averaging. There's a lot of noise and variability in the system. And so I've started more recently to divide this up more finely, and I can show you that at the end actually, but the gross behavior is pretty much encapsulated by these 3 groups. No sensitivity, some sensitivity, and largest sensitivity, roughly. Yeah, you get most of the picture from that. The smaller we divide it up, the more uncertain we are.
Just so that I don't get totally confused. So tremors propagate up dip and along the strike. This propagation has nothing to do with the earth tide. Once the tremors start, the tail of it is modulated by the ocean tides. The tides.
Roughly.
Is that correct?
Yes,
Following me correct?
yes, and most of the propagation is along strike.
And has nothing to do with the tides themselves. First,
Oh.
after the
Okay, that's a very good question. The front does not seem to be clearly modulated by the tides.
only the later behavior of the tides once the front.
Right. The front has its own stress driving it. Yeah. And actually this will be sort of addressed again when I show the model. Okay. So now, so this suggests that we can define a sort of sensitivity to tremor based on the factor in this exponent. And so, you should just speak up.
Yeah, so coming back to Victor's question, so actually there is sort of time in that picture, like there are the 3 time periods, but also the negative Coulomb stress refers to a point in the cycle, no?
Right. So every tremor has a tidal stress associated with it based on its location and its time. So for every tremor, I have a tidal stress change.
so we can associate the right part of the graph of the which color is that? The purple?
Magenta.
So the right part, we can associate that with the initial phase where you have more.
What? No, this is this
Yes.
magenta, it's the later phase.
Sure.
This is the initial phase.
phase of the later phase.
Not really, no.
Phase of the later.
It's lumping all these together.
Sure, that is exactly
Ah, so there's more right here at this 3 days. This is basically 3 days. There certainly are more at this time.
return period.
But in fact, if you look at this separately, it's still pretty sensitive. Sensitivity is not significantly different all along this tail, but we get more uncertain because of fewer tremors.
Yeah, because I mean the vertical axis of the right picture is the frequency of occurrence.
Yes, it's really a ratio. It's not a frequency, it's a ratio, and you can think of it as observed number of tremors divided by expected number of tremors based on the amount of time the fault spends in a certain stress state. So it spends about the same amount of time, roughly the same amount of time in this stress state as it does in that stress state. If we just look at 2 kilopascals, it spends about the same amount of time at positive 2 kilopascals as at negative 2 kilopascals. And down here, actually, we have probability distributions for the 3. They're also color-coded. So very little amount of time at these extremes, but we could say the same for 1 and -1. So even though it's spending about the same amount of time in this stress state and that stress state, it's having far more tremors, 3 times more tremor than expected, and here it's having roughly a third as much tremor as expected, because the very small Coulomb stress is enough to shut it off.
Sure. And what's the expectation?
The expectation is 1. So a ratio of 1 would be where the observed is equal to the expected, because this is the ratio of the observed over the expected. The expectation is based on the amount of time the fault spends in a given stress state. So yeah, this is kind of a complex histogram thing. Now, so I'm going to consider the shape, the strength of this relationship to be something I'm going to call the sensitivity. And this turns out to be about 0.6 per kilopascal is the units that come up. But now I'm going to show you a different measure, which is perhaps simpler, because I need to go to a different measure to look at spatial variations. And it's something I call consistency. And it is a fraction. So here we have a fraction. The color indicates a fraction. These are maps of tremor that happened when the tidal stress was positive, just positive, anything. Any positive value over here. So we'll just divide it in 2 pieces. And I need to do that so that I can get good enough numbers to compare this spatial variation. So this is all the tremor. This is the tremor divided into the 2 groups. And what we see overall is a difference between the 2 groups, consistent with what we saw before, the initial and the later tremor. We see a strong updip, that there's more consistency with tidal stress updip. And we also see for this initial tremor much less consistency, except in this region, which is a region where 4 of the 6 ETSs initiated. So in the region, so this is kind of a fine point. In the region where they initiate, we already have some tidal influence going on. Because that region was already very close to failure. And so the tidal stress is important and pushed it over the edge. Whereas in this region here, it wasn't so close to failure for 4 of the 6, or really all of them. And the thing that pushed it over the edge was a propagating slip pulse, stress from a transient propagating slip pulse. Okay, so people also might want to see the ratio of these 2 things, and it looks a little complex like this. This is the ratio of the later to the initial one, and there's some tendency of higher ratios of this to this up dip, and a ratio around 1 here in this initiation region. Okay, so now I want to return to the sensitivity notion, the other histogram, but break it up into with another dimension. So now I've got effective normal stress and shear stress. So instead of Coulomb stress, effective normal stress and shear stress, and the color is a ratio, and it's the ratio of the number of tremors divided by the amount of the number expected. So again, it's the ratio of observed to expected. And this is just for the later tremor only. And we can see there's more observed to expected up here where it's red, and it's a factor of 3 or 4 more. And there's less than expected. It's like about a half down here. And so I interpret this as a direct image of the Coulomb sliding line, the frictional sliding line, which should have this general slope because this is compression over here. And it has a very shallow slope of 0.1. in contrast with what Byerly's law would suggest of 0.6 or 0.8. So this is one of the pieces of evidence for a shallow, a low intrinsic friction. And to make this effective normal stress, I went back to our equation for normal stress and used the model 1 with the mean stress change. Okay, so we'll return to that. But what is the relationship of this to the histogram I was showing you before? Well, it kind of becomes clearer when you look at it in 3D. So now we've got normal stress and shear stress this way, and we're looking at it from the side, and this is the exponential behavior I showed you before. And essentially the figure I showed you before is a stack along this direction. Okay? So this also lets us know that I probably picked a good value of mu to stack along. Okay, so let's skip that. Okay, let's talk more about these two pore pressure models. So we have a model for the pore pressure, which is isotropic in nature, and a model with an anisotropic fabric, and we can ask which works better. Okay, so these are both for undrained conditions. There's some support for that, and this is appropriate for isotropic materials. This is appropriate for anisotropic structures or fabrics, which you might in fact think would exist on the interface. And this has been assumed in a lot of studies, for example, by Ross Stein and his coworkers. They typically assume this because in their studies of static stress triggering of one earthquake by another, or static stress triggering of aftershocks by a large main shock, they generally don't have the full stress tensor available to them. So it's easier for them to make this assumption of model 2, where this is the normal stress, because they don't have the mean stress change. Actually, they maybe could compute it, but they just don't. So they did this for a decade and a half, and then Coco and Rice looked at it to try to justify it. And one way you can justify it is with a model of a weak fault zone embedded in a stronger region. But when they looked at this using known properties from the San Andreas, they couldn't actually get a relationship as strong as this. This is actually an extremely strong relationship. It says that it doesn't matter, sigma xx and yy don't matter for the pore pressure. The only thing that matters for the pore pressure is the normal stress. And that sort of implies you have things are controlled. One way to look at it is also a fabric of large, flat, fluid-filled cracks aligned with the fault plane. So if there are really a lot of large, flat, fluid-filled cracks that have a very high aspect ratio, which these guys, Hawthorne and Rubin, proposed, then you can achieve this. But it's a very extreme situation where the fault has no strength in the normal direction, and in contrast to plenty of strength in the horizontal perpendicular directions to normal. So I usually bring a paper model, which I forgot to bring, and maybe you can just imagine it. I have a paper with a lot of cuts in it, long cuts that are parallel, and I find that I can easily deform the paper perpendicular to all the parallel cuts, and I cannot deform the paper parallel to the cuts. That's really what that model is saying. So we can ask which model will give a better correlation with the tremor, and that's what we're going to do. But it also turns out that if this were to be true, it implies a very high Skempton coefficient near 1. And this is also supported by some other research. So If that is true, we'll end up only being able to constrain effective friction, because this B near 1 is not well enough known, and if you have 1 minus 0.9 or 1 minus 0.95 or 1 minus 0.99, it makes too much uncertainty in this factor, so we get this, and if we want to go back and get that, we really cannot. But it's going to turn out the data actually prefer, of those two models, they'll prefer the isotropic model, oddly enough, or interestingly enough. So the way to distinguish them, well, maybe this is a little too detailed, but I'm going to focus on just a subset of the data sensitive to the difference between the two models. So, and I need to average over a range of friction coefficients and check different Skempton coefficients. And I'm going to prefer the model which gives me a better correlation between tremor and tidal stress. I know they correlate. Which of those two gives me a better one? Yeah?
When you talk about average over range of frictional coefficients, you're suggesting that the frictional coefficient is variable?
No. No, that will come clear in a moment. Okay, I'm suggesting that at this part of the study I don't know the friction coefficient. So if it turns out that model 1 has the better correlation, then we can go ahead and constrain intrinsic friction, like I did, for example, in that 3D, the red and blue 3D model that showed the exponential shape that we looked at from the side. That had model 1 in it. If model 2 is best, we can only constrain effective friction, and we can't make a figure quite like that, the one I showed you before. So we'll use the subset to decide which model we want, then we'll use the full tremor data set to constrain friction. It's a stepwise process. So essentially, it is going to be shown here. Okay, so here we're plotting the percent excess tremor. More than, so again, this is kind of the percent more observed than expected. So again, we're looking at how much more observed than expected happens. And the purple is for model 1, and the cyan is for model 2. And these are just times when these two different models give opposite signs for the Coulomb stress change. So it should be distinguishable. But this is just a subset of the times. In fact, not so much of the time. Okay, so to compare, we don't know mu, so we're going to pick a range of mu's. We're going to plot this percent excess tremor and do it for different Skempton coefficients from 0.5 to 0.9, which is a typical range. And what we see is that while there's variability, in general, in almost all cases, model 1 finds more tremor occurred if you assume model 1 than expected. If you assume model 2, fewer tremor occurred than expected. But going a little, so this is pretty much what I prefer for model 1. And if we were going to use model 2, we would pick this one, which also has the 0.9 Skempton coefficient, which it needs to be high for this anisotropic model to work. So it looks like model 1 gives a much better correlation of tremor to tides. So I'm going to go with model 1. I'm going to use a Skempton coefficient around 0.5, which is kind of in the middle. And I'm going to go ahead and compute. Now here I'm showing percent excess tremor, and it gets up to 30% more tremor observed than expected, and I'm showing it versus different friction coefficients. So now I've assumed model 1, I've assumed a Skempton, I've also assumed a minimum stress change for this, and I've got 6,000 observed tremors, and I've got the percentage of excess tremor more observed than expected, dropping off strongly as I increase the friction coefficient, which is another piece of evidence that the friction coefficient is well under 0.2 and probably around 0.1, between 0 and 0.1. And these values are much lower than laboratory values, as I said before. So recent studies in the lab on various minerals actually find very low frictions on a number of minerals. And I list some of them here: talc, saponite, graphite, thin films of smectitic clays, and recent studies. And here's a figure from Rick Simpson of anastomosing factoids, which is just such a weird term. But these are hard pods separated by weak, almost flowing, slippery serpentinite or clays. And this is his notion of the interplate interface. Okay, so my observation of a very low intrinsic friction for an average macroscopic piece of the fault that's, tens of kilometers in extent is consistent with some of these recent lab observations. So friction may not be 0.6 at all in this kind of a situation. So I wanted to make a simple model, and it's a stress versus strength model. And the strength are these distributions here. So what am I plotting? Time in days versus Coulomb stress. And the strength is going to be at each time will be randomly drawn from one of these distributions, which are Weibull distributions. And the stress is going to be computed from several pieces. And one of them is the actual tidal stress. That's the little wiggles on here. So here's a time series, and you see it's changing, just the little wiggles. And then we're going to need to add the transient stress due to the propagating slip pulse as we're propagating along strike. And rate and state friction and some arguments indicate that it needs to be asymmetric in shape and pretty high. So pretty high relative to the overall stress drop. So we start at a given spot on the fault, an average spot on the fault, at some stress, and we end at a stress drop, in this case, about 10 kilopascals less. I'd actually like it to be a little bit smaller. So we have this constraint on the ETS stress drop from geodesy, for example, geodetic modeling. We have the real tidal stresses and the range being rather small. And so what we find is that in order to generate tremor at the appropriate time with the appropriate sensitivity, these strength distributions must drop. An easy way to think about that is the breakage of mineral precipitates over the period between the large ETS events. So basically every 10 minutes I calculate the stress and the strength. If the strength is above the stress, I say a tremor occurred. If it's below, I say a tremor didn't occur. And this is a Weibull, let's skip that. And if I run this hundreds of times using different 10-day pieces of real tidal stresses and different places on the fault, real tidal stresses from different places on the fault, I get a synthetic which can be compared to what we saw before, which is extremely similar. We've got the initial period, the middle period, and the later period, and it's color-coded here, and we have the same behavior of sensitivity as before. So it's very similar to the observed histogram. So this does a pretty good job explaining that. Okay, so, no, I don't want to even talk about that because it's a little too complicated. Okay. So now I have the section at the end, but what time is it getting to be? Okay, so this is very brief. So what about what happens between the major ETSs? Do they evolve? So here we have another slide showing some major ETSs and inter-ETS between it, and most of them are very short and brief, and it's not practical to define a tremor front, so I lump them all together. And I have a concept that in the inter-ETS period, there will be a competition between healing in green and stress increasing due to tectonic loading. And here we have the tremor in the ETS, in the inter-ETS period. So there's a large ETS here off the figure and a large ETS back here. Another time distance plot where this is a year. And I'm dividing it into 3 groups. And you can also see this number is the cumulative number of tremor. It's increasing, possibly exponentially. Another inter-ETS period between 2 different ones is very similar to the previous one. And when I lump together these data for 5 inter-ETS periods, I find this consistency. The fraction is some value, it goes down, and then it goes up even higher. So it's low in this inter-ETS period. These are about a year, but it's a scaled period. And I find that the sensitivity, the slope, the fraction here, exponential, is up and then goes down and then up higher. So they're having a similar behavior. And then if we simply divide into more time periods, things get a little more uncertain, but now, again, one inter-ETS period, from after one ETS to before the next, the influence, the tidal influence is dropping, it's low in the middle, it's climbing toward the end, and this has the same general behavior, this sensitivity. So these 2 different measures are in agreement, and they can be understood as, in this middle period, strength and stress are far from each other. This period here, they get much closer to each other. Now there's some question as to what's going on right after the ETS. But this is the same image with the actual example of actual tidal stresses on it, and you see how variable they are with time because of the interaction of 5 different tidal components with 5 different frequencies. And we see that here toward the end, the tide is getting close to being able to push the stress above the strength. Okay, so this is zooming into 2 months and seeing how the ETS period stress versus strength might compare with the inter-ETS period stress versus strength, just for illustration. But, okay, so I'm going to just conclude that we've talked about the influence of tides on tremor during the ETSs. We've seen these 3 main conclusions: the exponential relationship, the evolution over a few days, the definition of 2 different ways of measuring it, and the intrinsic friction being quite low. Then I've started to look at the influence between the ETSs, and I see it does vary over that ETS seismic cycle, being lowest in the middle of the cycle, growing toward the end. And this kind of simple kind of strength versus stress failure model does a pretty good first-order job describing the relationship over the entire seismic cycle. So I'm going to stop there, and thank you.
Thank you, Heidi. Are there any questions? Yeah.
In the previous figure, Heidi, that one for instance, or there's another one just before when you show how both lines come together after a time, right? What's the law governing the green curve?
The law governing, okay, so it's a very simple assumption here that tectonic stress is building up linearly because of plate convergence, and the strength is building up logarithmically due to healing. And there's various studies, for example, of small earthquakes repeating earthquakes on the San Andreas that show a logarithmic show how they change logarithmically in time, and that's been interpreted that strength will heal. So we're talking about healing happening during the inter-ETS time and not being very interrupted by little bits of inter-ETS tremor. And that process is logarithmic. There's some evidence for that. So it's the competition between these two, or even if you go back to the more cartoon-like one, that healing tends to go as logarithm of time. It's a logarithmic function. Now, it doesn't fit so well right in this period here, which is an interesting thing that needs further
Sure. That's very
consideration.
Sure, I understand now. No, it's very nice, everything. So just one, thought. You're assuming that the pore pressure remained constant during the whole phenomenon.
Well,
You're taking, not necessarily, because the pore pressure is proportional always to the mean stress, which evolves with tides, so it's not constant.
there's pore pressure change and there's ambient pore pressure, and they're two different things.
Right, sure. But in any case, the only evolution of that component during the ETS in your model is due to tides.
That's right. And so a more comprehensive but also more complex model could consider an evolution of pore pressure during the 5 days, which I think is an important thing to think about.
I don't know. I don't know if it's because how much this would go into the same direction drawn by the observations. I don't know if it would help to explain or not what you are observing by introducing the pore pressure evolution given a pore elastic model, for instance. I don't know, but what it's, so you're assuming on drain conditions, because always the pore pressure change is proportional to the confinement. Okay, and the point here is this very nice functions you showed is a function of Coulomb failure.
Do you mean maybe go back, like here?
That one, yes, that's the theoretical expectation that is very
Right.
nicely compared with what you showed at the beginning, the observations. The last thing I would like just to better understand is how the expectation this is the normalized. These are normalized violin as with respect to an expectation value, no? For
Yes,
so
right,
how-
expected value.
right. How do you establish what's the physical principle to establish what is the expectation?
Okay, for this study, it's very simple. I expect the tremor, the number of tremor, so it's the expectation of the number of tremor if there's no effect of tides. If there were no effect of these tide changes, then I would expect for the tremor to simply be proportional to the length of time, the duration of time that the system is in a given stress state, say +1 kilopascals.
Sure, and what would happen if there's another phenomena, as for instance the diffusion of fluids? For instance, I don't
right. That's not addressed here.
know. Sure.
But that would be another thing to take into account.
Sure.
An extra
Okay,
piece.
I understood. Good. But very nice.
And that
very
might
interesting.
change this stress curve, this thin line. That might change that in some way.
Sure. Thank you, Heidi. Thank you very much.
If there's no further questions, we need to get out of here anyway because there's another talk coming up. So I think I'm going to cut off the discussion. Let's thank our speaker again, and there'll be more time to talk with her afterwards anyways. Thank you.
Okay, here is this. And this is yours.